Welcome to Dr. Jimny's Applied Calculus, Chapter 6, going into Section 4. Topic, implicit differentiation. So we have two words, implicit and differentiation. So implicit refers to things which are implied. Differentiation is the process of finding a derivative. So something about implied things and then trying to find derivatives. So if we have a function given, such as y equal square root of 9 minus x squared, then y is very explicitly defined. From any x we observe. So we can explicitly, given an x, find the y. So, but y equals square root of 9 minus x squared. Well, we could do some algebraic operations, square both sides, and then add x squared to both sides. So this would be for non-negative values of y. It's going to describe exactly the same set of ordered pairs. X squared plus y squared equals 9. For those y which are non-negative would be another way of saying that y is equal square root of 9 minus x squared. So they describe exactly the same thing. But in this one, we haven't solved, or we haven't explicitly said y is equal to an expression in x. So, describing the same thing two different ways. One is explicitly saying, given an x, compute y. The other one's not so explicit, but it's describing the same y's. Given an x, well, there is a y, according to this equation. So there's some expression that should give us y in this, but not explicitly stated. So it's implied in the equation that we have ordered pairs and that given an x, we could compute a y, but it's not explicitly stated. Or we might say y is somehow defined by that equation, but we haven't been explicit, so we say it's implicitly defined. So, in this particular observation, between the two possible ways, there might be other, but here are two ways to describe the set of ordered pairs. One's explicit, one's implicit. There are certain things nice about one. It's sometimes nice to solve, so we have a formula that's quick. But on the other hand, the one definition that has no square roots is a nice polynomial equation. So that can be rather nice. So we have reasons for explicit definitions and implicit definitions. So for the moment, let's look at that. So what if we didn't solve for y? In this case, we could, and we left this y equal f of x implied. What can we observe about the derivative, y prime of x? Notice that in the other notation, we're talking about dy dx. So what we're going to observe is that we have two sets coming from ordered pairs x and y, which are equal here. Derivatives would measure how things change, or relative changes. So if you have two objects and they change, well, if it's the same object, it better be changing exactly the same. So that means if we look at the related change of the left side of this equation and the related change of the right side, the derivatives that is, they should be equal. So we'll take derivatives of left and right side. We should end up with equal expressions when we do that. So now we will proceed by using derivative rules. Derivative of 9 is 0, since that's a constant. Derivative of any set of terms, we can break into separate terms. That's a property of derivatives. Any coefficients we could bring outside. In this case, we don't have any. And then apply other rules of derivatives. Oh, the observation, derivative of x squared is 2x. We have to be a little carefuler with the derivative of y squared, because it's really a composition in this setting. It's y depending on x, which we haven't solved explicitly, but it's implicit, a function of x. And then we've squared that. So it's the square of y of x. So it's a composition. So when we put in the derivative, it's going to require the chain rule. So it will be derivative of y squared, but the chain rule will also bring up the derivative of just the y. So some of these are directly functions of x, so the usual derivatives. Some are expressions in y, So in that case, every time we have the chain rule, we have an extra factor derivative of y. Now, in this implicit form, I've carried out as many derivative rules as I can, and I really can't go any farther. I have basic expressions without derivatives, and then just the derivative of y and nothing else. So at that point I stop and I solve for the derivative of y. So in this case, subtract 2x from both sides and divide by 2y. And I get a derivative, if I simplify a little, of minus x over y. So it's a different form. We could have taken the original square root, worked out some kind of a square root process. But this was fairly simple. I only needed derivatives of squares and then a little bit of algebraic solving. Come up with a different derivative. Looks a little different because I don't have it explicitly. Y is still implicit in this formula. If I had a particular point back on this curve, one point being 2 and the square root of 5, so 2 squared, square root of 5 squared is 9, so it's one of those, a value on the curve. Then the derivative would be minus 2 over square root of 5. So, but in this case, we could have done everything from the explicit form. But it was kind of nice that we didn't have very complicated derivatives here. Here we would have the chain rule with the square root and other things and end up in the same place, though. Now, there in that example we had a choice, but we might have something like 3 to the y times y is equal to x minus 2. Solve for y first explicitly. Well, not very practical here. There's no real known way to write that. So we're, in many cases, have equations we can't explicitly solve, so we have to leave things implicit. Somehow embedded in here are ordered pairs x, y, y depending on x. So to find the derivative, we will differentiate left and right sides, and that would be two equal expressions using derivative rules. Of course, this side is just an expression at x, and looks like that derivative is 1. The other side is written as a product of the function 3 exponent y and a function y of x. So if we apply the product rule, we would have one of those, say 3 exponent y with the derivative of the second in the product plus the other y and the derivative of the 3 to the y. Now we would have 3 to the y. This we can't do anything else. We have the derivative we're trying to find. But this part, 3 to the y, the exponential has a derivative, which is the exponential and a factor of natural log of that base. But it's, if I'm careful, that is, let's be, and check up above. I didn't transcribe more of these. Okay. So derivative in terms of x, so y is a function of x. So it's 3 exponent y of x. So again, we have chain rule. And so in each of these, where the variable, the y, and the x don't match, we have one extra factor, dy dx. And so at that point I can solve for that derivative dy dx. This is usually not too hard because it's always dy dx to the first power. So we either have terms with a dy dx factor or things without them. So we separate the two and then divide. So we have the derivative without ever having to explicitly solve for y. Of course, the derivative is somewhat implicit. Given x, we don't know exactly what y is, but if we had a point on the original curve, we can find that particular dy dx.